Okay, how about this first question about condensation on a cold glass of water? What we got?
The water vapor transfers energy into the cold glass and slowing down the water vapor. It turns into a liquid.
Okay, so H2O gas hits cold glass and does that sound good? So it had a certain amount of energy in its gaseous phase. It lost energy. It lost so much energy, it's no longer a gas anymore. It's moving slow enough. The amount of kinetic energy transfer has gone down into the water. So what's happening to the glass and the water in the glass? Those guys are speeding up. They warmed up. So really it's just, I have something that's moving at a certain speed and its kinetic energy is greater than the kinetic energy of the object that it ran into. So it transferred some of its kinetic energy into that object, thereby equalizing or more equalizing kinetic energies. Try the Lewis structure for selenium oxide. So selenium, how many electrons, valence electrons do we have here? Yep. So we got 18 electrons here. So I've got selenium in the middle, and then I have an oxygen and an oxygen, and I've used 2 of my 18. You'd use all of them. So how do you want to do this? A double bond to both sides? Okay. Now what?
Two that's on each oxygen.
Why do I not like that?
It doesn't matter, they all were 0.
No, they weren't.
I thought they were.
Why is that bad? Tell me how many electrons the selenium is seeing in this format. Count that again.
10.
There you go. That's why it's bad. So selenium doesn't have sulfur or phosphorus' ability to do this. So, sorry, this one's not right. So what if I take away one of these double bonds? Because double bond is what allows us to conserve electrons. So I don't want to conserve electrons. I need to use up 2 more. So I take these 2 electrons that we had in that double bond, and I don't know, I put them over here on this oxygen. Now what do we got? How many electrons have I used? All 18 of them, right? Okay, so I've got a valid Lewis structure. Everybody's seeing 8 electrons. I'm asking about the VSEPR structure and the molecular structure. So is there a VSEPR structure? There's lone pairs of electrons on the central atom, so there's a VSEPR structure. So what I have is a selenium with a lone pair of electrons and an oxygen and an oxygen. So I have what for my VSEPR structure? And if I draw it again, sans the electrons, what do I have for my molecular? Yep. That work?
With that, with the dash line of the VSEPR.
Don't need a dash line. There's only 3 things connected, so those 3 things are all going to be in the same plane. Oh, I'm sorry. You mean on the Lewis structure?
Well, no, that,
on this.
yeah, the dashed line that indicates that the double bond's bouncing back and forth.
You don't draw that on any Vesper or those only go on Lewis structures. So he's right. You could totally say that this double bond is over here, remove these 2 electrons, remove that double bond, and throw another couple of electrons over here. This is a this has delocalization. There is resonance here, but it doesn't affect the shape of anything. It does affect one thing. What will it affect? Bond length. So I don't have like a short or a long bond here and then a shorter bond over here. That's not the case. I've got 2 bonds that are like in the middle length. But that's still not going to affect the shape of the structure. It's still going to be bent and still going to be trigonal planar. So pi bond, sigma bond. So the pi bond electron is just electrons from p orbitals. And the sigma bonds are electrons that either are just a straight s, like in the hydrogen atom, or some kind of hybridization, like in the carbon atom where I've got an s and maybe 3 p's, or an s and 2 p's, or an s and a p. And so there's some s characteristic that's been added into it. If I take like the sphere and then and add these things all up, this is going to constitute 4 sigma bonds because I've added in some s into each one of these p bonds, these p orbitals. What else do you want to say about them being different? The pi bonds are accessible, very accessible to anything that might interact with the molecule because those electrons in that pi bond are in the exterior of the molecule. So you can interact with them easily, where the sigma bond electrons are located in between the atoms. So there's a measure of protection from the atoms themselves to keep those electrons located between those atoms. So anything that's got a double bond is going to be much, much more reactive than things with single bonds. For this one, I was thinking something like for a sigma bond. For a pi bond. So we can see that it's interior, and we can see exterior. How many electrons are here? 2. How many are here? 2. It's a bond. Even though the pi bond is in more than one place, it's still only composed of 2 electrons because there's 1 electron in this p orbital, 1 electron in this p orbital. There's one electron in this hybridized orbital, and there's one electron in that hybridized orbital. So what shape do we have with an sp3? The reason you should know that it has to be a tetrahedral shape is what we're saying is there's one s electron and 3 p electrons all going in different directions. So this is something connected in 4 and what's the sp2? And this atom has bonds going in 3. If this is a carbon atom and it's got to be connected 4 times, where's the 4th bond? It's only connected in 3 different directions. So where's the 4th bond? Okay, but where is it located? It is a double, but where's the double bond get located? Say again? Did you say interior? No, these 3 here, the sp3 or sp2, those are interior bonds because they're s characteristics, because it's an s added to 2 p's. So those are the interior electrons. So where's that pi bond? Easiest thing to say would be above and below. It's got to be going in the same direction as one of the original 3 bonds, above or below that bond. And the sp? Linear. And this is 2 and again, same situation here, above and below, and then in the front and in the back for the other 2 p electrons. Okay.